we're here in the last, at least like assigned module of like content that I think, and for the most part, I kind of pick and choose things that I think will be important and interesting for this. But then module 5, when we finish up, will be your own application. So taking a piece of the course or maybe a few ideas and applying it to something of your own. So this one's all about like energy and momentum methods. So we're still dealing with like motion and causes of motion, but instead of thinking about like just how does F equal ma, we're going to look at like new ways of rewriting the same equations, but get to descriptions of impulse like F delta T and work, where it's like F times that delta R, like how far something's moved through a given force. Yeah, so we'll look at a few different methods there, and even rotational, like angular momentum, and how that can help describe motion, that kind of thing. Oh, so I skipped right over. But jumping into homework 4, the first question is from chapter 4, looking at a spaceship in deep space, 10 to the 4 kilograms. So this large kind of, I feel like Star Destroyer is too big. Maybe X-Wing. You think that's like 10,000 kilograms? Traveling through deep space. And the thrusters have been anti-aligned with its speed of 50 meters per second. Want to fire the thrusters for a certain amount of time to bring our spaceship to rest in absolute space before disaster strikes. So the question is, how long do we need to fire the thruster so we stop the spaceship? This is the problem that we're working on. I want to know, like, what's your first thoughts on this? Like, how, like, identify what are the steps you want to take and how to plug in and get to that final time, like delta T. How long did you fire the thruster? And then I'll share like my thoughts on it too. But. What are you thinking? Okay, yeah.
So we're given that the kinetic energy is 1/2 mv squared. Okay. So if we integrate force times distance graph, that force times distance is work. So until that force times distance graph equals 1/2 mv squared, that's what I'm trying to say.
Okay. What would that one give you? What have that? Like if you set up a work energy relation,
how would you define the distance?
Yeah.
Maybe we're looking at equations to define time.
Yep. Yeah, that would work. Yeah, anti-line is like velocity is going this way, but thrust is that way. Yeah. And then deep space. So the assumption of deep space is that there's no net gravity. Maybe there's gravity from big stuff, which was what we could assume for the most part. Gravity. All right, one thing that warms my heart. First thing people did was draw a free body diagram. Like, yes, now we're getting it. Now we're in business. First thing you do, start drawing arrows. And sometimes it seems like silly. Like, I don't know if it feels like this sometimes, but it's like, okay. Like, that's my free body diagram of just, and depending on where you said velocity is, I'm saying like maybe it's moving to the right, and I'm saying thrust is anti-right, anti-thrust. Sometimes that seems silly, but the beautiful part about this is that I've just proved that F equals ma. I've just proved that a is constant because F equals ma, and F is constant. So ma has to be constant. Mass is also constant. So I can say like ma is a negative F over m. Now I can solve for a. I can plug a into constant acceleration like kinematic equations and go from there. At least that was kind of, it seemed like some people were trying to work towards that, of like, what is my equation of motion? And then I can integrate it and get to a solution for like position and velocity. How does that sound? Does that seem like general thought so far? Yeah? All right, let's try one other method, because now I'll introduce like a new tool. It's similar to like free body diagram, kinetic diagram, just like a little different, but it helps for problems like this or problems where there's like explosions or impacts. So it's called, and yeah, so this, at least in this step, we would say this is step 1, step 2, A equals. Step 3 is that V of t is V0. It's, at least that seemed to be where people were thinking, but not everybody. Like some people had different kind of thought. So impulse momentum equation is always that a change in momentum is due to some force applied over a certain amount of time. This could be an average force, it could be an instantaneous, like huge force, but this relation is always true. And if there's no external, like I think conservation of momentum, do you remember learning about that in physics? That one's true if there's no external impulse. But if you're saying like, hey, I hit this thing with a baseball bat, it's not that the baseball has to maintain a 0 momentum. It's that baseball bat created impulse, and now baseball fly, baseball go far. And we can represent this with same way that we did with like vectors, like drawing up vectors and how they add up together. We have mv1 plus f delta t equals mv2, which is 0. and they're all lined up, like kind of one-dimensional motion. I mean, it's in space, like maybe it's pointed in some weird direction, but for the problem, it's either moving forward or backward. What is this? This is like 10 to the 4 kg times 50 meters per second minus 100 newtons times delta t is 0. So in the first problem, and creating an equation of motion it'll always get you to the same step. The only difference when you use like impulse momentum directly is that you already have force and time, force, time, and velocity. Like they're all included in one equation. So kind of in a two-step process, we get to a solution. And newtons are kilogram meter per second squared, right? How long do we need to fire the thruster? What do you think? So we have like 10 to the 4 over 10 to the 2. So 10 to the 2 times 50. How many? 10 to the 2 is 100 times 50. 5,000, yeah. So over an hour of thruster time. Takes a while. It's a big ship. And 50 meters per second is not slow. And so this is also nice because impulse doesn't always have to be like a constant force. We could solve for like what was the average force over that same amount of time, and it would still be the same answer. It's like if the average force was 100, then this is how long it would take, or vice versa. Like we only have 30 seconds. What's the average force? So maybe we ramp up really high and then ramp down, but as long as our average force over that time is what we need it to be, and that's good. Kind of cool. Good to have like new tools in the tool belt. Sorry, I skipped right ahead. But move. Good questions. I didn't give you time to formulate questions, but it's okay. Good. All right, this problem is going to be like a lot of like little steps, and we're kind of looking at like some theory about angular momentum. When is it conserved? When is it not? So here we have these two reference frames. This O prime is moving away at a constant speed, and attached to that O prime is a spring, and this mass is moving around. We're not solving for what the motion is, but I can tell you, based on how this thing is set up, it's going to be some kind of like ellipse around that O prime. So it's almost like an elliptical orbit. Like if it had no initial like theta direction speed, then it would just bounce back and forth. But here it's rotating around in a circle, but the spring is always like trying to bring it back, moves faster the closer it gets, and then spins further out. We have some kind of elliptical thing going around there. And we want to think about like someone that's watching this kind of setup and just fixed versus someone watching them drive like on a train. They're watching this experiment kind of going by. Yeah.
While the frames move to the right, those springs would same about.
Yeah, yeah. Yeah, so the motion from the observer, it would look like it would kind of be like spiraling like that as we like watched it go by. Depending on how fast we're moving, right? Like maybe it would just look like it's zigzagging or something, but. And what we'll do, again, I'm trying to like lay this out because there's a lot, we're going to be doing a lot with this. First step is just defining what are the, when we say this thing has a position or a velocity, like what does that mean? Like what's the minimum, like its degrees of freedom? How do we describe that? And the goal with that is that we should be able to cancel that stuff out and say like angular momentum is a constant value in our O prime frame. But then in our O frame, we should find that angular momentum is not constant. So we're comparing a moving frame to a fixed frame, and where can we say angular momentum is conserved? Again, we'll do a lot of stuff, but most of it is like simple stuff. Like to start off, the first 3 steps, there's no real like math involved. We're just applying definitions. So we're just choosing how to describe motion. So in our first step, think about the person that's traveling with this little elliptical orbit experiment, and they're watching it. How do they describe the motion? Like, what is the definition for position and velocity of this object? And I'll leave it at that and see. Yeah, that's the question that we're trying to answer. I want to see what's your interpretation there. What do you think? I describe like position and velocity.
Just looking at the positions of the right or no?
Yeah.
Does it change? Or is it the same thing?
So it's going to be like, we don't know what it'll look like, but it'll be some kind of like ellipse, like moving around in a circle. Or not a circle, an ellipse there.
Using polar coordinates or?
We can use polar coordinates, yeah. What does position look like for polar?
Well, the angles change.
Use that angle. Okay. even like, dude, who's here? What is motion? So those would be like our position. We could do that if you were trying to break it into like B1 and B2 elements. So first step is like when we're thinking about what are the coordinates, like we're being asked like how do you describe geometry of motion? So one of the things you should think about here is like, all right, how many degrees of freedom do I have? Like, how much, what am I trying to describe here? Do I just need to describe like left-right motion? Is it moving in a circle? So all I need is like what angle it's at and R is constant. What do we think? How many degrees of freedom does a point mass have?
The point mass, I guess 2, since it's
2?
It would be changing angle, but since it's all left, so it would be changing the R value.
Yeah, so R could be changing and theta. So somehow we need those two things. So polar coordinates works like that. The Cartesian works just as well in terms of like this is a definition for position. What is, so in a polar coordinate system, what does a position vector look like? R comma theta, but in terms, what's like the unit vectors? Like if I have, is it radius? Do I move one radius along one direction and theta along another? Like X and Y? It's different, right? There's something, we definitely need, like R and theta are kind of like polar coords. We have 2 degrees of freedom, so we're tracking both its position through time and its angle through time. So position for a polar coordinate system is just how far is it from the origin, so what is the radius, along that unit vector that is ER. So in this case, I'm saying ER is pointing up this way. And that's it. That's all we're being asked for. So that's why I was saying, like I tried to say, like, all right, don't jump into, like, we're not trying to do like a bunch of math and figure out like how do I integrate these equations. We're just trying to set up what are the ground definitions that we need for this. All right, so if that's our position, what is velocity? Where's this thing going? I remember, like, once you're in a polar coordinate system, the definitions for position and velocity and acceleration, it's always the same. It doesn't, so it's something that we can look it up. So let's say, go through the textbook, flip through, find what is the definition for velocity in a polar reference frame. Here it is. It's r dot along that ER plus r theta dot along that E theta. And that's just all we really did here was recognize like, hey, this thing seems to be moving circular-ish, so let's choose a polar frame and write down the definitions for motion in a polar frame. And that's all we need, at least to get through that first step. And I'm going to redraw our two reference frames here. We have E1, E2, D0T to get to, B1 and B2. Let's do this. So I redrew like just kind of at least the stuff that I think is important for what is position and velocity with respect to O. So now we're thinking about like someone standing still watching this thing fly by. How do they describe position velocity? We already said there's only 2 degrees of freedom. So we can use time as part of our definition, but we shouldn't need to introduce like a new X and a new Y, right? Because there should be there's always a function of time that relates O and O prime. They're like fixed in time for every point in time.
Because I think these still well, they're still tracking that. Yeah. Okay. Would you just collect this the distance from what's he using or this be careful the space that you want to from this. Yeah, that makes sense to me. Since vectors, you can always like add them up as long as you add the components, right? Okay. Okay.
So if we want those, we want events along our
Okay. Yeah. All right. Yeah. Okay. So get it back into X and Y coordinates. Yeah. Okay. Yeah. And then you have, is it still CR or is it a new radius that you described? Yeah. Okay.
So I saw like, or at least kind of like talking a little bit about this. I didn't check in with everybody, but some of the thought process is like we could still track this in terms of like R and theta, but use the Cartesian reference frame since we're moving along an x-axis for this second one. So we could say this is actually our cosine theta along that B1 plus our sine theta along that B2 if we're trying to get everything into one like one frame where we can add everything up. So then where do I add that V0t to describe, because that's kind of the relative position, right? Because we're just really here what we're saying is that the position of P with respect to our fixed person, O, Oliver, fixed Oliver versus moving Oliver, O prime, Oliver, 2 L's, so there's like the relative position, the relative motion of like the frame of reference plus the relative position within that frame. So I can call this one V0t along, let me leave it in E1 for now. And then I can put this one as RER. Can I replace E1 with B1? Is there a difference between E1 and B1? What happens if you take a vector and you move it somewhere new? Does it change the magnitude or the direction? No. So if two unit vectors are in different places but they're both pointing same direction, they are the same unit vector. There's no difference between E1 and B1. Same thing for E2 and B2. It is the same unit vector. ER is different. That one's changing over time. But I can write it out like this. I'm just saying, like, this is my relative position, and that's my relative, like, spacing of my coordinates. What about for velocity? What does that one look like? Just based on how I wrote position so far. This one's a definition of like relative velocity. And we know we already decided what this one was. And then the other one, this one's given. So I can erase these. I'm mixing and matching unit vectors. Is that okay?
They're the same, that's fine.
If they're the same, are they the same? ER, B1, E theta. So it is okay, but as long as you just remember, like, B1 has, or ER has a B1 and a B2 component in it. and E theta has a B1 and B2 component in it. So if we're doing cross products or dot products, we just have to remember that B1 cross ER, we just have to do that cross product out and then figure out what it is, something like that. But it's okay to mix and match. Like, we're just trying to figure out what are the definitions here. If you want to put it all into one, like either B1, B2 or ER, E theta, you can do that, but it's okay to like have a couple of different reference frames. All right, so now we're going to draw free body diagram. So we went through all the work of like defining position and velocity. And again, it's just applying definitions, like not trying to do math to figure out what they are, just trying to say what's the minimum number of things that I need to keep track of. That's what our definitions are trying to tell us. Now, what does the free body diagram look like? I'm gonna erase the spring, but what does our free body diagram look like for? Yeah. Oh, did you already draw it? Or? Oh, okay. Yeah. Yeah, just on that moving. Yeah. Usually what happens, like, springs always stretch, depending on how fast it's spinning the circle. Usually it'll be like stretched, and the farther away it gets, the slower the rotation is. Then it starts, the spring like pulls it back closer, and as it gets closer, it starts spinning faster. So usually it's stretched, but different levels of stretching along the way. Yeah. Including the spring, yeah.
Yeah. Could be circular or it could be super stiff springs. Yeah. Does the free body diagram depend on the molar? No.
So this thing, is a spring.
I mean, force is a force. It's just like,
And this is a.
I guess the root is just the motion. Yeah.
And like, it's spinning. Oh, that's. It's like. So if you flip more to, push it down.
Force of the spring goes right to O prime, right? Because the spring is connected at that moving point, O prime, and then it's connected to our mass. Gravity is acting like down into this table, so we don't have to say like it's not trying to like pull it down along that B2 axis or something. There's just, so if we look at the out of plane, then maybe we could say there's like gravity down, some kind of normal force up, but that's it. Force of the spring. We just have to figure out like where it's pointing. Does it matter that we're using polar coordinates or Cartesian coordinates to describe motion? Does it change our free body diagram? No?
It's the same force, just you're describing it.
Yeah. So once you have like a vector, that vector is just, it exists. Like it doesn't matter how you kind of turn your head and look at it. It's always still describing the same magnitude and direction. And that's it. Yeah, free body diagram. Just force of the spring pointing down that way. And then in the book, the next thing it asks you to do is find angular momentum, but we just drew the free body diagram. So I want to do moment first. Do you remember what definition for moment is? If I want to look at the moment around O prime on P, so we're looking at like the sum of the forces on P at a given position of P/O prime. So what are what's like all the torques that are created around that moving O prime point? Yeah.
It's like a perpendicular component of force times its radial on, like to that coordinate.
So like I think that one was like R times F times sine alpha. Something like that. If you have like, do you have a position with a force applied to it, magnitude of where it is times magnitude of the force times the sine of the angle between them? Is that what you were remembering? Something like that? Is that trying to gauge with a lot of blank faces, trying to gauge like, is this the way it was done, or is this like voodoo magic? I mean, I remember like seeing this equation and not knowing how to use it at one point in my career. I don't use it very often anymore. What's another way of getting like the perpendicular component? If you just want things that are, if you want to take like what are the two perpendicular components of this of these two vectors? That's maybe it's a weird question. So another way we can say that is R crossed with F, the cross product of position and force. That is the moment. Like all the moments produced are the cross products. And in general, it's the same idea of like, all right, just take the component of force that is perpendicular to that moment arm, and then do it that way. So we're taking what is the position of P O prime crossed with what is the force of the spring.
Those are like relative position that are prime are P prime. Yeah. So that would be like that first term, and then cross the part would define that force of the spring. Okay. We'll be piecing together for this part. Okay. Is theta have like a P theta direction? Okay. Yeah, like so if you're using like theta hat, ER is this way, theta hat goes this way, then velocity is in R dot that way, R theta dot that way. So that's why I asked total speed with the combination.
All right, spoilers, it's 0. Nice when stuff is 0. But I know it's 0 because this is RER, like that's our position, crossed with a negative K, and I can put any value I want, like R minus L0, it could be a nonlinear spring, it could be all sorts of stuff. But it's in the ER direction. It's always pulling it back along that ER. That has to be 0, because if I have a force this way and position in the same spot, position along the same axis, it creates no moment. There's no moment created in the system, at least for O prime, for that O prime direction. All right, cool. Thanks a lot. Back on Wednesday, wrap this one up and try to jump into next problem.